Hello students, welcome to Unit 1 Notes, Section 1-3. I'm going to start by going over this warm-up. In an effort to save time, I'm going to start going over it now, but feel free to pause the video at this time and try this on your own. So the warm-up question is asking which of the following functions grows faster, and explain why. Normally I would ask students in class to make a prediction on which one of these would grow faster. Some students would say that f of x equals x to the fourth would grow faster. Some students would say f of x equals 2 to the x would grow faster. And the final answer is that this one, f of x equals 2 to the x, grows faster. And the reason well, here, let's actually graph it. X to the fourth and 2 to the x. Let's take a look. X to the fourth. X to the fourth, and then 2 to the x. And what you see here is 2 to the x starts off pretty slow, right? And at first, it is not winning. X to the fourth is winning. And then we see that it does take over and win. And x to the fourth is not winning. And then we see that x to the fourth wins again over here. Sorry, I'm trying to click on it. We have x to the fourth that's definitely takes over. And a lot of students would say, well, there you go. There's the proof. X to the fourth is growing way faster. At 1.7, it's almost at 10, and at 1.7, this other function is at like 3. Yeah, and that definitely makes us think that it's going to grow faster, right? Look at this. I mean, hello, x to the fourth is already at 20 when x to the fourth here is at 20, when it's at about 2. And for this one to get up to 20, it takes it double the amount of time. It's at like 4. And then we're going to start to zoom down here. Whoa, look at 200. Say, Mr. A, how much further do we have to go for the blue one to win out? I mean, here's proof right here. We're at like 4. We're not even at 4, and we're at 200. This one, unfortunately, had to go to, what, 7? Okay. Whoa. Okay. I'm still not winning my case here, am I? At 10, we have 10,000. It takes this one 13 to get to 10,000. Let's keep going. And there's the proof. Finally. Right here at about 16, 16 is where it all changes. 16 to the fourth power and 2 to the 16th power are equivalent at 65,536. And what happens? The blue one takes over. The blue one takes over for a very long time. How long? Well, forever. And you can see this here as I'm zooming out and changing it, that the blue one absolutely, when given enough time, will always beat out and win. And why is that? Well, a very simple concept. We call it exponential. This is a exponential function. Exponential, as you may know, will always beat out any other type of function. Exponential literally means that it grows exponentially. It is doubling every single time. If this particular one is doubling every single time I move one more unit over. Yeah, and so x to the fourth here is actually slower. We can say it's faster for a while, but ends up being slower in the end. Faster at first. It grows faster at first, but then slows down as x approaches infinity. All right. And so this lesson today is simply about exponential functions. Growth, decay, applications of exponential functions, and the number e. That's a special number. It's approximately, let's approximate it at about 2.7183. It's a really cool number. Certain things grow at that form of an exponential, 2.7183. Okay. Now, let's take a look here. What is exponential growth? Well, let's say that in 1996, I invested $100 into a bank account. And that bank account was getting 5.5% interest. Whoa, that's quite a bit. We don't see that anymore nowadays. We see more like 0.5% or 0.05%, nowhere close to 5.5%. But at one time, they used to offer a lot more for you to put money in the bank. But also, the rates of other things like mortgage rates were higher. Now, mortgage rates are much lower, and so are the dividends that they give you for leaving money in the bank. So, if I ask you $100, what do you have at the end of 1 year? You would say 105.50. What you can't say is, what do you have at the end of year two? You can't just double this and say, well, I get $10, that's $11, so I have 111. I'm sorry, instead of $5, I then have 111. Well, why don't we have 111? I just add $5.50. I add $5.50 again. Don't forget, you have to add $5.50 in that type of percentage to the $5.50 that you made in your first year. So what does that look like? Well, it's when you take 100 and you multiply it by 5.5, and then you take 105 and take that and multiply it by 5.5%. Or look at how they wrote this. They wrote this really nice. 1.055, that's for your 5.5%. 1 just stands for the initial value, 100. So 100 times 1.055 is 105.50. Multiply it again by 1.055, that's 1.055 squared. You don't get 111, but instead you also get an extra 30 cents. Wow, don't spend that all in one place. But now you take 111.30 and you put it in here and we multiply, so I can either take 111.30, multiply it by 1.055, or take the initial 100 and multiply it by 1.055 to the third power, so 3 times. So what I'm doing is I'm increasing first $5.50, then 5.80, then 6.12, then 6.46. And so it might not look like a lot, but you're already making almost in 4 years an extra dollar for that same money based on that same rate. And it doesn't look like a lot, but exponentially, this will actually get to be pretty high. Let's see in 20 years. No, let's look at 20 years what that same $100 would be. So, let me go to let's see if I can do this in the calculator. Let's do 100. And I'm going to put 1.055 to the 20th power. That would actually be 291. So in 20 years, let's do 20. Yeah, can we do 21 years? In 21 years, your money would triple. It doesn't, again, doesn't seem like a lot, but let's say it's more than $100 we're dealing with. Let's say it was $10,000. Now you have 30,000, right? The average, the stock market, it's not a it, it's not a stationary thing. It goes up and down, but on average, it gives about 7 to 8% yield per year. So yeah, there are some years with 20% of growth, and then other years with negative 20 years of growth. But on average, it produces about 7%. That means that if you invested $10,000 for, I don't know, 30 years, that same $10,000 would now be worth $73,000 in 30 years. So it's really cool just looking at how fast this grows. Um, and right now, I mean, we're currently in a pandemic, and we're seeing the increased numbers. If we were to go to, let's see, um, let's go to COVID cases. Let's see, Reuters is there. Where is a good? Let's see. Here we go. Let's look for a graph here. U.S. trends. Here we are. So here's a great example. When this first started, it looked like nothing was happening, and then all of a sudden, it took off. Look at what happens from January 22nd all the way to April 2nd. I mean, until we changed our behavior, we had what was definitely a exponential function here. The the amount of cases were, oh, here we go. The moving average is increasing, right? You see this? 200, 400, 800, thousands. So here's the 7-day moving average: 6,000, 8,000, 10,000, 12,000, 14,000, 20,000 cases a day, 22,000 cases a day, 24,000. And remember what happened a little bit in March here, March 13th of last year is when we closed schools. And the reason was because we were afraid of this happening. And what happened was we were already a little bit too late. And that's March 13th right there. The average was 240 cases a day. And that moving average, what they're doing is they're averaging the prior 7 days. And unfortunately, we should have stopped it maybe over here. But this was the result. And remember, it takes 14 days for things to start to change. And so right around here, this is where we made massive changes nationwide. I mean, Rhode Island might have been one of the first states to stop, and it took a few other states to catch on, and then we were able to what they call flatten the curve. And so as you can tell, you have this reduction here, and then again, exponential welcome to summer, right? Here's June 15th. Everyone's out of school, everything opened up, and here's our daily cases. And, we don't know what the future holds, but these are definitely exponential spikes based on human behavior. And now we have students returning back to school. So we'll see if this curve will flatten when that happens or what. These are also many after many holidays, right? So Labor Day, you might have some increasing. After the 4th of July, yeah, that was your 2 weeks after the 4th of July right there. Okay, so enough of exponentials, but those are exponentials in the real world. They are represented by a base to a power. So in this case, our base to a power. So a is our base, and x is our power. Our power with an exponential is always, our power is always an exponent. I apologize. Our power or exponent is always a variable. Okay, it doesn't have to be the variable x, but in this case, we are graphing on a Cartesian coordinate plane, so it is. Here's a little note here. 2 to the x grows this way. 2 to the negative x grows this way. All right, we could also throw a negative in front of negative 2 to the x, and it would grow this way. And negative 2 to the negative x would grow this way. Remember that 2 to the negative x is equivalent to 1 over 2 to the x. So what's happening is, as I approach infinity, it's becoming 1 over 2 to the infinity, or 1 over infinity. And when infinity, that's like a million, billion, trillion. So 1 over a trillion is almost nothing. It approaches this idea called 0. It gets closer and closer to 0, which you see happening as you have 2 to the negative x. Okay? Yeah, I mean, there's other ways to flip them and graph them and whatnot, but let's just stick with the basic ones for now, and let's see what the lesson has in store for us. So here, example 1 is graphing an exponential. I've already graphed it for you. Let's save some time. What we have is a vertical shift. We have a vertical shift of negative 4. And we have 3 to the x, but we also have a 2 in front of it. And that's not really doing anything other than making it grow twice as fast than 3 to the x would grow. All right, so let's think about this. Can I put in any number for x? Looks like x will continue to go that way, and x will continue to go that way, both to the left and right. Doesn't look like it will stop. I mean, it will go to the right. It's just, it will go very, very high in terms of y, but it can still go to the right. It is still going to the right. So our domain here is all real numbers, negative infinity to infinity. And our range can't go forever. It looks like it can only go as low as this right here, negative 4, which is what we call an asymptote, right? We know that this won't keep going any further. We are stuck at negative 4 being our asymptote, but it will go up as high as we want it to go, because it just never stops. So our range is negative 4 soft bracket to infinity. It's not a hard bracket because it will never get to 4, but that is definitely one of our restrictions. So for an exponential, you're definitely going to have an asymptote somewhere. The question is where. In this next one, it looks like we have the same idea happening here. It looks like we have an asymptote. You know what? I'm just going to copy this one. Looks like we have an asymptote right here. And where is here? Well, it looks like it's at 5. Huh. Well, take a look. Isn't 5 my vertical shift? So that might tell you a little bit more about the function. So the vertical shift is right there. And it looks like that is where the asymptote shows up. Looks like, whoops, I don't need that line. Looks like that goes on forever. Looks like it stops up there at the asymptote. And then it does look like it goes on forever for x. I can put in any x I want. Again, it's going to grow very quickly downward, but we can still put in any number for x and then evaluate that. And then it goes on forever in the negative. So our domain, again, is negative infinity to infinity, and our range is going to be, it comes up from negative infinity, and then it stops. It never reaches it, but it definitely stops at 5. It won't get up to 5. It'll stop before 5, but that's about all we got. Okay? And now it wasn't asking for the domain. It was asking for the zeros. So this is just, I didn't really answer the question here. It says find the zeros of it. So the 0 is going to be equal to, so we want to know where is y 0. Well, 0 is equal to 5 minus 2.5 to the x. So what I'm going to do, and that's the thing is, when it's asking zeros, it's asking when does f of x equal 0. We'll substitute in 0 for f of x, and then we'll be able to solve for that. So let me add 2.5 to the x to both sides. And I get 2 point, I'm just trying to make everything positive because we want to make sure that we're dealing with positives when I have a exponent. And I'm going to now find, I'm going to solve for x. Now, how do I solve for x? I can't add, subtract, multiply, or divide. This is an exponent. So what I need to do to both sides is I need to log both sides here. So I'm going to do log. Let me pick a different color here. We did orange. We did not do green. Okay. I'm going to log 2.5 to the x, and I'm going to, oops, I'm going to log 2.5 to the x, and I'm going to log 5. And so the x will drop down. So I'll have x times log of 2.5 equals log of 5. And then I'm going to divide both sides by the log of 2.5. I'm running out of room here. Let me move this up. You know what? I didn't need the domain and range. Probably should have answered that. But I'm going to throw it over here so that I have room to answer this question. And so now I'm going to divide both sides, and I'm just going to write it as log of 5 over log of 2.5. And that is going to be approximately log of 5 over log of 2.5. Let's see, log of 5. Log of 5 divided by log of 2.5. And that's about 1.756. Can I copy that? No, I can't copy that. 1.75647. 75647. 1.75647. 75647. That's good. Okay. And that is our answer for what our 0 was. And it does definitely fall within our domain. Okay? Now, I do want to show you one other way you could have solved this. When you get here's another another way to solve. When you had 2.5 to the x equals 5, what you could have done was it's called log base 2.5. You could have log base 2.5 of both sides. What it does is it kind of saves, I don't have room here. What it does is I don't want you to get it confused with what is happening over here. So what it does is it kind of saves a step here, because there will be what log base 2.5 of 2.5 will actually wipe itself out. It will actually cross it out because it's an inverse. So you simply get x equals log base 2.5 of 5. The x will drop down and then you're done. Okay, so let me just put this in here. So that separates. Yep. No, I'll just leave it. And what you'll see here is log base 2.5. So instead, my log function is going to have a base of 2.5, and it's going to be of 5. And you notice they're the same answer, right? Because when you divide log, this is a property of logs. Division allows you to actually use the denominator here as part of your base. Okay, so that's going to be the same answer. And it's about, x will be about 1.75647. That's just another way of doing it if you want to. All right. I don't know how to separate everything. That's all right. We'll just leave it. Okay. So here are some rules for your exponents. If you multiply two bases, two of the same base, you can just add the exponents. So 4 to the 8th times 4 to the 12th is 4 to the 8 plus 12, which is 4 to the 20. Here we have 4 to the 8th over 4 to the 12th. It's going to be 4 to the 8 minus 12, or 4 to the negative 4th. Remember, you can cross these out. Remember, if you have a couple up here, you cancel with a couple down there, and you have your remainder. You write either in the numerator or denominator, depending on which one has more. Okay, a to the x to the y. Don't forget, it's the same as a to the y to the x, which is the same as a to the x times y, a power to a power, right? If you have 4 to the 2 times to the 3, it's really 4 to the 2 times 4 to the 2 times 4 to the 2, which is really 4 to the 6th power, because you're going to break those all up, so you multiply. All right. A to the x times b to the x is the same as multiplying a and b and bringing it to the x power. So in this case, 2 to the 4th times 3 to the 4th is the same as 2 times 3 to the 4th. That's the only time you're allowed to mix bases, is if the exponent is the same. Other than that, you got to keep them separate. And then same thing here, you can, well, not the same thing, but you can apply the x to the numerator and denominator. All right. Now, exponential decay is what a function like this would look like. A decaying function is something dying or something dissipating. Exponential decay has, you've heard of things like half-life. So um, when a nuclear power plant produces waste, that waste has a half-life of radioactivity. So the molecules are bouncing around. They're throwing off either protons or electrons, neutrons, and those are those um, have uh, radioactive properties that slowly, die down over time. For instance, Chernobyl, one of the most famous radioactive explosions, they're still saying that the nuclear waste there is nowhere near its half-life. It's still radioactive to this day. So here's what happens with exponential growth and exponential decay. The function y equals k times a to the x. This is just some type of constant. Doesn't matter what it is. But we also have an a to the x, which is our exponential. And it's a model. If a is greater than 1, we're going to have some type of exponential growth. And if a is between 0 and 1, notice it doesn't say negative, but between 0 and 1, we'll have decay. So let's just model that real quickly. Let's do 2 to the 5th power. Okay. Oh, sorry, 2 to the x. And you notice that when x is positive, it's going to be growing. And then if we do, here, let's do 2 to the 1/2. To the 1/2 x. I'm sorry, I'm putting in the wrong numbers. When a is greater than 1, here we have 2 to the x versus 0.5 to the x. Let me fix that, my apologies. And you notice that these go in 2 different directions. So let me try to bring this back to where we should be. Is there a reset? Here's a reset. Boom. There we go. So you notice in red, here's where your base is positive, growing up, right? And then here's where it's negative, going down. I can't click on it. It won't let me click. There we go. Here's where it's going down. Okay, so that's, again, you'll notice that 0.5 to the x is not the same as 2 to the negative x. Well, it is, because look at how I moved the 2 down, right? It almost became 1/2 when I moved that down. So the negative exponent here really just lowered that 2 to be in a denominator. And it's really the same thing as 1 over 2 to the x, making it 1/2 to the x, making it a number that would result in exponential decay and not exponential growth. Okay, predicting the United States population. So here we have some data from 1998 all the way into 2003, and then we have all of these population in millions, and then it looks like we have found a ratio here. So we have 1.0116, 1.0111, 1.0102, 1.0102, and then 1.0097. It looks to me like 1.16%, 1.11%, 1.02, 1.02, 0.97%. It does look like over time, population's not actually increasing as much as the time goes on from 1998 all the way to 2003. And there could be reasons for that. There, there could definitely be reasons based on the economy, culture, generational changes, people not having as many kids in their families as they used to in the days of farming, and different things like that. So normally what I would actually have you do at this point is use a calculator to calculate the amount of to, to create an exponential model. But we don't actually have that ability because we're not allowed to use our graphing utility calculators. So I will show in class how this is done. Um, I will demonstrate using the graphing utility on my computer in class, but for now I will do it on my graphing utility calculator that I have with me here. So I'm going to click the stat button and click edit. And I'm going to put in 0, 1, 2, 3, 4, and 5, and that's going to represent the years starting with year 1998. Then I'm going to put in 276.1 for millions. That's how many people we had in year 0. And 279.3 for year 1, 282.4 for year 2, 285.3 for year 3. We have 288.2 and then 291. And I go back into stat and I'm going to calculate what's called so I click stat and I go over to calc and I scroll down all the way to what's called a exponential regression. It's number 0. So I hit exponential regression. Look. And I just tell my calculator to calculate it. So here's what it gives me for an equation. It says, again, I'll show you this in class. It says it says y equals a times b to the x power. And it says a equals 276.32900987. And it says b equals 1.010544408. Now, I'm not going to really want to use this at all, but it's saying that we could put in 276. We can actually type this into the equation. And instead of doing that, I'm going to simply copy and paste it. Second stat, give me 1 second. I'm going to copy and paste. If I can remember how to do this. Yep, so y equals variable, statistic, equation. I'll show you this all in class. I copied and pasted it. And when I put it into the table, it gives me a whole bunch of data. And so the question now is, it's in the XY table now, if X, so X and Y. So here's your 0, 1, 2, 3, 4, 5. What is 2010? 2010 is going to be year, add 10 years to 2000, and so it's going to be year 12. So at year 12, I have 313.39. So what this is suggesting is that there will be approximately 313,390,000 people in the U.S. in 2010. It's not a perfect science. Remember that there are generations that had way more people than others. The exponential growth increased. So as we get to the end of that generation, we lose a lot more than we might be gaining, and vice versa. So it's not a perfect science, but based on this small set of data, we were able to predict that there'd be about 313 million. Now, with us being in 2020, if I add 10 more years to that and I look at year 22, it says 344 million. Well, we haven't done the census yet, but the suggestion is that there's closer to 335 million, so we're off by about 10 million people. Again, because I think this rate is slowing down. It's a combination of the rate slowing down and other factors that are going to lead to less population. So, all right. Modeling radioactive decay. Suppose the half-life of a certain radioactive substance is 20 days and that there are 5 grams present initially. When will there be only 1 gram of substance? So in this case, if we do y equals 1/2, we're dealing with half-life, and the substance is every 20 days. So I'm going to say time over 20. And the reason for that, well, you know what? Let me keep it more simple. What I'll do is I'll divide time by 20 later on. So I'll say it's y equals 1/2 to the t, because whatever I initially start with is going to be, we're looking for when there's 1 of it, and it's having a half-life every 20 days. So let me also put a 5 in here, because my initial amount is 5, and I'm reaching a half of it every 20 days. So I'm going to, when I get a number for t, that would actually represent 20 full days. So I need to multiply the number by 20 when I'm done, right? Because really, t represents 1/20th of my time that's there. After 20 days, 20 over 20 would equal the number 1. And 20 over 20 equals 1, so that would make time 1, which would be 5 times 1/2 to the 1, or 5 times 1/2, which would make 2.5 grams left. So I just need to make sure I multiply by 20 later on. I could incorporate it here, but I think it's going to be a little bit more simple if I don't. So the question is, when will I get down to 1 gram? So 1 gram is 5 times 1/2 to the t. So I divide both sides by 5. I get 0.2 equals 1/2 to the t. So I'll call it 0.5 to the t. And so I'm going to log base both sides. So log of 0.2 equals t times log of 0.5, because the t will drop down. And I divide both sides by log of, 0.5. And I get t is equal to log of 0.2 over log of 0.5, and log of 0.2 over log of 0.5. Remember, I could use the shortcut for this one. Two point three two one nine. 2.3219. 2.3219. $2.3219. Don't forget, we have to multiply this by 20. So time is how many days? 46.44 days. 46.44 days. There we go. So think about, if I do 46.4 and I divide it by 20, I'll get 2.3219. So 1/2 to the 2.3219 will give me the number 0.2 about. and 0.2 times 5 is 1. And so that's when there'll be 1 gram remaining. All right. Okay. This last one, nope, I still got more. Here we go. Use the population here to estimate the year 2000. This one will be definitely a little bit better of a prediction. So here we're going to put in, let's see, we can put in 0 and 10 and 20 and 30 and 40, 50, 60, 70, 80, 90, 100, 110, and we want to go all the way to 120 using the data set. And let's see. Oh, you know what? They didn't even use that. They used 12 instead of 120. It's still going to be the same. And when they ran their projection for 2000, they get using your graphing utility calculator, they get 308.1712. So again, you could have used 0 through 120, and that's fine, but you would have had to go up to 120 to get your data. In this case, they kept it a little more simple. They did 12 instead of 120, and it's still going to give you that same result because instead we called it 12 decades later instead of 120 years. So it looks like that one's all set. I could enter it, but to save time, it says compare the result with the actual 2000 population, which is approximately 281.4 million. Well, it's way over, right? It looks like it's almost over by 30 million. So, yeah, it's over by 27 million. Again, this is a trend of economies and of generational changes, and everything does change over time. It could be a generation prior to us that made up a lot of population and then is no longer around with us. So yeah. All right. The number E, it's a special number represented by 1 plus 1 over x all to the x. And as x increases, you'll notice as it goes to 6, 7, 8,000, 9,000, 10,000, as it approaches infinity, it approaches this number, and feel free to highlight it here, 2.7183 or 2.7182812828. And this is a really cool number. A lot of things happen in the real world that follow this particular sequence of growth. And one thing we can use it for is compounded continuously. Things that are compounded continuously use this particular model. It's called PERT, y equals p times e to the rt, where e is 2.7183, r is a rate, t is time, and p is a principal amount. So a lot of times when we're trying to figure out if interest were being compounded continuously, we would use the number e. All I want you to know is that the inverse of E is ln, so the ln of E is 1. It's the same as saying log base E of E is 1. And that's it for our lesson. So feel free to ask me questions on it. You can also work on your homework now. And yeah, good luck.